Okay. I would like to introduce Subhajit Goswami from the Tata Institute of Fundamental Research, and he will talk about equality of critical parameters for GFF level set percolation.
Thank you, Nina. Thank you, everyone, whoever is joining, and thank you, the organizers, for giving me the opportunity to talk. So the work I chose to talk about today was appeared in the archive during the beginning of this year. And this is based on this is done jointly with Duminil-Copin, Pierre-F and Franco Severo. Now, before I dive into the core topic of the talk, let me set the stage by recalling some relevant facts from Bernoulli percolation on hypercubic lattice. So this is a graph, we'll be concerned about. All the models we'll be talking about today are defined on ZD, in particular, D bigger than or equal to 3. So as we know, so the Bernoulli percolation, what you do is that you declare every edge, or in a variant, every vertex of the lattice to be open, independently with the probability P, which is a parameter of the model, which is called the density, also called the density. Then the open edges that resolve from this experiment induce the random subgraph of the lattice. And the question we ask there, the first question is that whether or not this random subgraph has an infinite cluster, by which I mean an infinite connected component. Now, since the models are stochastically increasing with respect to the density parameter P, it's not difficult to posit that there is a critical parameter PC, such that below that, we do not have an infinite cluster, and above which you have an infinite cluster. Okay, and in this case, actually, it turns out to be also unique, but that's a deeper fact actually than just monotonicity. Now, while the monotonicity tells you there exists a critical parameter, it doesn't tell you automatically that this is non-trivial, by which I mean that it's strictly between 0 and 1. And although this is the case for Bernoulli percolation on the lattice, and it's not particularly difficult to prove, but when you encounter a percolation model, be it a dependent percolation model, unlike Bernoulli percolation, or even Bernoulli percolation on very general graphs, not the lattice, then the first question to ask is whether or not the phase transition is non-trivial. And I'll actually touch upon this problem also in the course of my talk. Okay, now, while this gives us a very broad level picture of the phase transition, we would like to understand finer properties about the clusters, in the configuration in finite regions. How big are they? What are their shapes? What are their properties as graphs as compared to the underlying lattice, and so on and so forth. Now, there are two auxiliary critical parameters that are relevant for addressing questions like that. The first one, which I denote here as PC tilde, and the notation is by no means standard, demarcates what I would recall here a strongly non-percolative regime, by which we mean that in this regime, the probability that a point is connected to a box of radius L around it decays exponentially in terms of the radius. And one can see one immediate consequence of that is that all the clusters in a box of size L in this regime would be at most logarithmic in L, in the radius, with high probability. Now, while it's not difficult actually to prove that PC tilde is bigger than 0, okay, just do a basic first moment argument for P small enough. There's a much more difficult problem to prove that this regime extends all the way up to the critical point. That is that PC tilde is actually same as PC, the critical threshold defined earlier. And this was proved actually in late 80s, separately by Menshikov in 86 and then by Aizenman-Barsky in 1987. And in more recent times, Duminil-Copin and proved by very elegant argument this property for generic group invariant Bernoulli percolation on general graphs. Okay. So then let's go to its supercritical analog, what we call here as a strongly percolative regime. This is demarcated by the so-called the slab percolation threshold, PC slab. So what happens here is that in this regime, we percolate through a two-dimensional slab of sufficiently big width. And this turns out to be, for Bernoulli percolation, the regime that enables you to run renormalization arguments that are so instrumental in understanding the supercritical regime. And here I list very few and by no means exhaustive properties about that you can prove in this regime. One of that is that you have a macroscopic ubiquitous cluster in a finite box, whereas the next big cluster will be at most logarithmic in size with a high probability. Then also can prove that the intrinsic distance in the infinite cluster is comparable to the Euclidean distance. And then also, of course, that the truncated two-point function, and just notice that this actually reduces to the two-point function, that the connectivity function in the subcritical regime decays exponentially fast, and among others. And just like the PC tilde, again, it's not difficult to see that PC slab is actually less than 1, because, for example, for any p above the threshold of Z2 would work. But again, it's a different problem, a much more difficult problem to prove that this is actually the same as PC. And this was proved by Grimmett-Marstrand in this 1990 paper. And an analogous result for the the cousin of Bernoulli percolation, which is the random cluster model, was proved by Fiori-Bodino in 2000s, early 2000s, 2005, for the case Q equals to 2, so which is the FK Ising model. And to the best of my knowledge, I'm sorry, am I back again?
Yeah.
Yeah, sorry, something just popped up on my screen.
Okay, no problem.
I'm very sorry for that, sorry. Anyway, so what I was saying that, so it's known for FK Ising model. And to the best of my knowledge, actually, to that, the only values of Q for which an analogous result is known are basically Q equals 1 and 2. Okay. So now, what we want actually, so we basically want to ask the similar question, okay, that whether these three a priori different critical parameters are indeed same for a different class of models. And I'll introduce that model, this class of model, with a representative that's probably most historically relevant and most interesting, arguably. But this is not the model we'll be talking about today, okay? But this is a good one for motivating the problem. So this problem refers to the fragmentation of a discrete torus by a random walk trajectory. And this goes back to the work by Benjamin and Stillman in 2008. So here, let's consider a discrete torus, d-dimensional discrete torus of side length n in dimension 3 and higher. And it's a known fact that the cover time of the random walk on the torus scales like n to the power t, the volume times log n. So if you run a random walk until that amount of time, with a very high probability, almost every point will be touched by the random walk. Now, a very interesting picture emerges if we instead allow the random walk to run until a time proportional to the volume of the torus. So let's fix a parameter, a positive parameter u. Let's run the random walk until time u times n to the power d. And let's look at, so then what happens in this regime, that there will be a positive fraction of the vertices which will not be hit by the random walk. And we denote this set, the complement of the trajectory in the torus, by v and u. V refers to the vacant set. The naming is clear. So this defines a family of monotonically decreasing random subsets of the torus. So therefore we can ask about its percolative properties as u varies. Just a small thing, and this will be also the case for the model I'm going to finally talk about, is that the direction of monotonicity is reversed now, unlike in Bernoulli percolation, where as the parameter increases, the model becomes stochastically larger. Here actually it's the opposite. And this will actually be reflected in the way we define the critical parameters. Yeah, just let us keep that in mind. Hopefully that will not be too much inconvenience. Okay, so here is a simulation due to David Windisch of this configuration corresponding to n equals 200 against 3 values of the parameter u. So if you see the rightmost picture, which corresponds to a bit higher value of u, so the red one indicates the largest cluster, and the blue one in the vacant set, and the blue one the second largest. So you'd see that this picture resembling the strongly non-percolative regime in Bernoulli percolation, where all the clusters are small. Whereas if we look at a smaller value of u, you see that a picture which resembles the strongly percolative regime in Bernoulli percolation, where you have a big cluster, macroscopic cluster, which is kind of ubiquitous. And the next cluster, the second largest cluster, is very small in size. And yeah, and this value of u is, I think, a bit closer to a critical point where you have a more balanced picture. So at least I think, okay, this picture was proven by Benjamin in this beginning paper for high enough dimensions and high enough values of u. Okay, sorry, small enough values of u. Now, big breakthrough happened when in this seminal paper in 2010, Snidman introduced an infinite volume model, denoted here by VU, that describes the local limit of these configurations. And just like these VNUs correspond to the complement of random walk trajectory, this vacant set corresponds to the complement of the so-called random interlacement trajectories. And I'm not going to give a precise definition for random interlacement, that are not very relevant, but just to roughly speaking, this is a Poissonian ensemble of bi-infinite random walk trajectories defined on the lattice indexed by a time-like intensity parameter u. Okay. So now that you have an infinite volume model, one can similarly define the critical parameter u star t. And like I said before, the first question to ask when you see an infinite percolation model is that whether there is a non-trivial phase transition. So which in this case means whether this critical parameter, this parameter u star d, is finite and positive. And that was proved in these two papers by Snidman and Vladis. And then actually people started studying this percolation model and several properties of that. And a lot of effort also went to obtaining better and better coupling between the vacant set and and the vacant set corresponding to fragmentation. And the goal was, to translate, to have an efficient dictionary to translate the results obtained on this side to the fragmentation side. Okay, now actually, before I move on to the model we'll talk about today, let me tell you what actually distinguishes, what sets this model apart from Bernoulli percolation, for example. So, and this is actually captured by this display. So if you look at any value of the parameter, any positive value of the parameter, and look at the covariance between the states, whether they're open or not, at two vertices x and y, the decay, like a Green's function, in particular power law, with respect to the distance. But what I would like to draw attention to is that this is not really, it's actually a bit rather slow decay. What I mean by that? So if you fix one vertex, let's say x to be the origin, and you sum the covariances of all the vertices in ZD, then it's quite easy to convince yourself that this sum diverges. So if you think about this implication in plain words, what this means is that if you condition on one vertex to be open, we open up on an average infinitely many additional vertices, okay, and which hints towards the long range of dependence inherent in this kind of models. And another thing which makes it different is that unlike Bernoulli percolation, this model doesn't enjoy much flexibility. I mean, what I mean is that you cannot locally modify configurations paying a finite price. For those who are familiar, it's called the finite energy, so-called finite energy property of percolation models, which we have, for example, also random cluster models. So the canonical example, I think, is given by this situation, which is that, let's say, all the neighbors of a vertex X are actually open in the vacant set. That means they have not been hit by any interlacement trajectory. Then that automatically forces the vertex X itself to be vacant, because in order to reach X, you have to pass through one of its neighbors. So what I mean to say, all of this actually, so make this kind of model very challenging, but at the same time makes it a very fertile ground to develop robust techniques for answering, for addressing the classical questions in percolation theory. Okay. Now, let me go to the model we'll be talking about, and this actually has similar in properties, but it's a bit more technically tractable for reasons that will be clear in the later part of the talk. So this refers to the so-called level sets of Gaussian free fields. Okay, so what do you mean by that? So this involves this object Gaussian free field, which is known to many, of course, is that, so for our case, it's a centered Gaussian process defined on the lattice, okay, in ZD, and whose covariance is given by the Green kernel, the Green's function for the simple anomorph ZD, which is essentially the number of expected number of times a simple random walk starting from X will visit Y. Okay, so how do you define a family, a monotone family of percolation models using a Gaussian field? Well, you just look at its upper level set. So fix a height parameter H, and just look at the set of points where the field is above the height H. Okay, and you can again convince yourself from this property that the covariance between two vertices being open in this model again decays like this function. Okay. Okay, so again, remember that this is a monotonically decreasing family because this becomes rarer and thinner as H increases. So, well, the critical parameter you define in terms of the, well, just in an unusual way, but just reversing the the order. Okay, so before I talk a bit about this critical parameter, let me also introduce another one, and there is going to be here why. Okay, so here is another one where, okay, which is basically the parameter above which the box-to-box connection probabilities decay to zero along some subsequence of scales. Okay, and what you can see is that this is definitely, this regime where this happens is definitely within the subcritical regime. So in particular, A star star is bigger than or equal to A star, because if you have infinite cluster, these probabilities will be positive, uniformly positive. Okay, now let me come to the known facts. And again, the first question to ask is whether the critical parameter is finite. And and remember that here the parameter space is basically the height to anything between minus infinity to infinity. Now, if you remember okay, probably the first or second chapter of Grimmett, the way you actually prove that the critical, for Bernoulli percolation, your percolation threshold is between 0 and 1. So the proof of the existence of a subcritical regime is quite simple. It's just a simple fast moment argument. Whereas the proof of the existence of a non-trivial supercritical regime requires a bit more deeper ideas, surrounding cut sets and things like that. And usually on general graphs, this is the problem which is more difficult. Okay. But here, actually, for this particular model at least, it's kind of reverse. It turns out that using the Markov property of Gaussian free field, you can actually prove that A star 3, actually A star for all dimensions, is actually bigger than, so it's minus infinity. In particular, actually, even you can prove that it's non-negative. So that if you again remember that the direction is reversed, so it means that you have a non-trivial supercritical regime. Whereas it's actually quite difficult to prove that it's finite. I mean, that there is a non-trivial subcritical regime. And this was proved actually back in 1987 by Lebowitz, Brickman, and Myers for dimension 3, and their argument was very three-dimensional that could not be generalized to higher dimension. And thereafter, it lay dormant for nearly 25 years. And then what actually, based on the story I have been told by Pierre, is that there's this birthday conference of Varadhan, I think in 2011, when Lebowitz posed this problem of proving the non-triviality of his transition as a challenge for all them, and Stillman was there. And then in 2012, he and Pierre-François Rodriguez published this paper, but they proved a stronger result. What they proved is that indeed A star star, this parameter, which is known to be bigger, at least A star, is finite. And they further proved that the two-point function in this regime, when H height is bigger than A star star D, actually decays stretch exponentially. Okay, so like a bit like what you have for the strongly non-percolative regime in Bernoulli percolations. So therefore, I justifying the name. Now this exponent has been shown to be actually improved, and then it works for random, both random interlacement as well as this model to be basically an exponential, 1 in dimension 4 and higher. In an upcoming work with Franco, Severo, and Pierre, we show that we find the explicit, very the precise last division exponent for this probability at all points of the critical point, actually. Now, so this is the picture. Potentially, there is a gap between A star and A star star. And what is known actually before our work between, about the relationship between the two was that both of them are asymptotic to the same number for large dimensions. Okay, their asymptotic values are the same. Okay. Now, let me come to the supercritical analog, like the strongly percolative regime. And here, I unlike the Bernoulli percolation, slab percolation threshold is really not the right quantity, right definition to look at, because, as you can see, as you can guess, the long-range dependence inherent in the model. So what we define here actually is really kind of and there are other Euclidean analogs in the literature, but really going for the strongest possible definition you can have, okay? So what we call here is a local uniqueness at a height h and scale L. So this even consists of two parts. The first part is about the existence of a macroscopic cluster, okay? Whereas the second is about saying that any two big clusters in your box actually can be connected in a twice bigger box. It's about uniqueness. And for people who are familiar with this kind of things, is that to just strike immediately, these are the kinds of events that you would want to trigger your renormalization arguments, because you see, if you have this event in a family of adjoining boxes which make a connected set, then the clusters, the macroscopic clusters within each one of them, they will actually join together and make a bigger cluster. Okay. Yeah. So okay. So then what we call is that which is defined. I would say that the phi strongly percolates above the height h if for all scales the probability that if you don't see this even is at most stage exponential in the scale. Okay, and we defined, because this property is and then we defined my threshold for the strongly percolated regime, which we call it h bar, as the maximal height below which the phi strongly percolates. And from this kind of argument, this gluing argument that I hinted at, it will be clear that that below h bar you have an infinite cluster. Okay, you make an infinite cluster, and in fact, it's also clear that it will be clear that it's unique, because otherwise you will contradict this property in infinite many scales. Okay. Right. Okay, now, of course, I can, we can define things as we wish, but nobody is saying that, this is probably whether such a regime exists. In particular, whether, well, we know that supercritical regime is, but whether h bar is bigger than minus infinity. Actually, much stronger is known, result is known. So it was proven by Lebowitz, Pierre-F, and Rodriguez that this strongly, this h bar is actually positive for strictly positive, and it actually answers many related questions, and all dimensions bigger than or equal to 3. And then there have been several works, where you prove, properties like similar to the supercritical Bernoulli percolation in this phase, which I have listed here. And also in a more recent series of works, large deviation bounds for disconnection probabilities between the blow-ups of compact regions have been obtained in this regime, in this works here. Okay, so there are a lot of things understood in this regime, like the stage exponential decay, and in some cases exponential decay above a star star. So the question is, of course, okay. So before we go there. Well, whether these two parameters between which a star is sandwiched are indeed same. Now, to study that, actually what we have to do is that, we would like actually, to have as much properties as possible, information as possible about the behavior of this model between these two a priori different thresholds. Okay, and for that purpose, h bar, the definition of h bar, the way we defined it, is not very convenient. Why? Because it's a very strong definition. So it tells you a lot, because that's the way it has been chosen when you are in this regime, but it doesn't tell you that much when you are not within this regime. unlike the definition of A star star, you see, this is a quite unique definition, and this tells you, quite a bit actually about the connection probabilities when you are below H star star D. Okay, because that's the advantage. So we'll try to find a similar analog of H bar. Okay, and here it comes. Let me read it out in words for you. So what is this H tilde saying is that below this height, what we have is that if you take any box, sufficiently big of radius L, and you place a very small box, a subpolynomial size box at the center, and then you look at the connection probability between this small box and the boundary of the box, then it is at least 1 minus some epsilon over L to the power T, okay? Where epsilon can be made as small as possible by choosing L peak, okay? If you have any questions, I can stop and I can clarify it further if anybody wants. But okay, but why L to the power D? The reason for that, why actually there is this factor 1 over L to the power T, or epsilon over L to the power T. Well, this is exactly the one that you need to run a simple union bound argument to say that the very high probability, on average, you have a high proportion of the boxes of such small boxes inside your big box are connected to the boundary. Okay, so they have a lot of almost all a very good proportion of the boxes like this that are placed inside this big box are indeed connected to the boundary. Now, in the particular, okay, in the limiting case, if imagine they were all points. So this actually kind of resembles what in Bernoulli percolation known as almost everywhere percolating subgraph. So let's say you have a box and every point you have in a subgraph where every point is connected to the boundary. Then there's this paper by Itay Beniamini and Vincent Tassio, which is called Homogenization by Splinking, which proves that if you have such a subgraph, then by applying a tiny bit of splinking, no matter how small, you can actually connect these clusters, these boundary touching clusters, into a unique cluster, okay? With a stretch exponentially high, with a probability that is close to 1 by stretch exponential, okay, with a very high probability, you can connect them into one cluster with arbitrarily small splinking. And so then actually using that, you can obtain events that will give you this kind of by renormalization scheme, sophisticated renormalization scheme, the events involving hair. Okay, okay, this is very vague, but the thing is that their argument is for Bernoulli percolation, and there are a lot of technical obstacles to adapt their argument for our case. And but it's true with and we can prove that for all d bigger than or equal to 3. And notice that the other part of the inequality again, that if you are in the strongly percolative regime, you actually have this property that just follows by the kind of gluing argument I just said. Okay. Okay. Fine. So what we have here actually after this proposition that, well, I have replaced H bar with H tilde. Okay, so the situation now I have here is the following. So I had H star sandwiched between these two parameters. Above H star star, I know a rapid decay of the truncated 2 point, the probability of connection. Also, similarly below H tilde, I have, from known results and things like that, I have a rapid decay, the truncated 2 point function. In between, what I know. So that's a regime we're interested in, and hopefully we want to be able to show that it doesn't exist. So let's look back again at this definition. So now what I know about this regime, first of all, since I'm bigger than H tilde, I know that I have just by from this definition, that for all scales, I have a polynomial lower bound on these disconnection probabilities, okay, throughout this regime. Similarly, since H is also less than H star star, I have a positive, uniformly positive lower bound. If you look at its complement, if you imagine the complement of this definition basically says that the box-to-box crossing probabilities are uniformly bounded away from 0. Okay. Then using this argument used by Raphael Sarf in 2015 in the context of bounding arm exponents for Bernoulli percolation, we can actually obtain the following, that the point-to-point, the probability of connection between 2 points are also bounded below by polynomials. And this argument actually, although done for Bernoulli percolation, just requires FKG and lattice symmetry. So both of which we have. Okay, so what do we have now? We have for let's say if actually in the case these two numbers are not the same, we have throughout an interval a polynomial lower bound on both the connection as well as the disconnection probabilities. These are more actually reminiscent, should be reminiscent of the kind of what do you expect at the critical point, right? Critical point of the percolations. Okay, so the question is, of course, whether these two intervals, whether this interval really exists. Any questions so far? Okay. Okay, so now let me, so in order to make our way into the idea of the proof, so let me first talk about a relatively easy version of the problem, which is obtained by truncating the range of Gaussian free field. What I mean by that, and in this case actually Gaussian free field compared to random little estimate comes very handy. So as you know, well, by the definition of Green's function, this is you can decompose it into a sum of transition kernels, L-step transition kernels of a lazy random walk, each of which is actually a non-negative kernel because they are actually event step transition kernels for a random walk on an extended graph obtained by including the mid edges. Anyways, so since they are non-negative, one can define in Gaussian field, a centered Gaussian field, the covariance kernel given by the L-step transition probabilities. And since the random walk cannot travel, right, more than L steps in, more than a distance L in L step, these fields are finite range. Okay, so if you take 2 points further than L apart, or 2 sets with the further than L apart, they are independent. The fields restricted to them are independent. Okay, so then what happens? Okay, so what happens is that, well, your Gaussian free field is in distribution same as the independent sum of the psi-Ls. So now actually it's clear how actually we'll truncate the range of phi. Well, we'll just take the sum, partial sum. We'll just basically truncate this infinite sum. Remember, if this was infinite, this would be phi. I'll just truncate it at scale capital L. So that would give me a field which is range at most L. And as L increases, these fields approximate my original, the Gaussian free field locally very well. Actually, yeah, the difference of the variance decays like a polynomial. Okay, so fine. So now we can similarly define, this percolation problems with phi L instead of my phi. So you just look at the level sets of phi L, and let's call these corresponding parameters for phi L to be just H tilde L, A star L, and H star L. And so we ask the question, well, whether they're same. Now you will believe that to be true because well, they are finite range, so they're probably most likely they're like Bernoulli percolation. So, and it turns out to be the case. They're indeed same. Okay. And the proofs actually follow by adapting the existing arguments for Bernoulli percolation. For the supercritical part, we adopt the argument of Grimmett-Marstrand. But I should mention that for the subcritical part, we actually use the OSS technology recently developed in Duminil-Copin, Raufi, and Tassion. Just a small caveat, but it shouldn't bother you, that actually, for just purely technical reason, we didn't actually prove this thing for this, the levels of the phi L themselves, but rather perturbed version of that. just to have some technical, just to go around some technical, unnecessary technical difficulties, but it should not, morally affect any of the argument in the rest of the talk show. We just assume that they are levels as a phi. Okay. So at this point, we might be tempted that, well, okay, fine. We have this property and we have these candidates which locally approximate your field. So maybe can we just pass to the limit, maybe, and somehow, some magical way, this properties, this will just pass over to phi, okay, by some means of like comparison or whatnot. So before we actually go there direction, let me give you a spoiler that even at the end of the talk, you will not know anything in that direction, okay? But just to pay tribute to the historical succession of ideas that eventually led to the proof of this result. So let's start having a dig in that direction. Okay, so, well, what do we mean by a proxy, one approximate Southern? Okay, one would be the following, very naive, that probably, this model can be stochastically dominated by, and it can stochastically dominate both directions, basically, this model by, shifting this height parameter in an appropriate direction by a very tiny amount. The amount will shrink to 0 as you increase L. Okay, now, that's not true. And the way to see that, easiest way, is that these models are actually stochastically incomparable. So if you look at, for example, the probabilities of a ball being open or closed in this model, these are like Bernoulli, and you'll have the exponent, the last division exponent will be volume order, okay, volume of the ball. Whereas in this model, there will be like a capacity order, okay, actually up to a log factor, but yeah, so which is like, for a ball of radius r to the power d minus 2. So that's not happening. Well, then actually you'll say, okay, of course, but we don't need that. We just need a particular class of events. We're just concerned about probability of connections between two sets. Yes, so in that direction, let me present to you this proposition, which indeed seems to say that, yeah, you can actually achieve what I was saying if you just replace the condition of stochastic domination or by comparison of connection probabilities. So you just look at the probabilities, the box-to-box connection probabilities, and they seem to be indeed comparable by a small enough change of the height parameter with an additive error that decays very fast with respect to the size of the smallest ball. So why did I say then, you'll not know any comparison, or you'll not know if they are comparable? And there, I'd like to point you to this particular restriction. So this is a conditional result. So this result is true, holds true, only when H is sandwiched well within this interval, H tilde and A star star. And I'll try to convince you now by a short argument that this actually implies that these two numbers are equal, thereby reducing this interval to empty interval, and subsequently this statement into an empty statement. Okay. So eventually you don't prove any substantial comparison statement. So what is the proof? Okay, let me just show one side. Let's say this interval is non-empty. So I take epsilon to be a very small fraction of the gap of the interval, and take A0 to be the middle point. Then let us try to apply 1, okay, to the situation where H is equal to H0 plus 2 epsilon, okay, and capital R is just the twice of small r. So this just corresponds to the case, for which if you remember, you have this one, okay, this situation, to reduce probabilities of this kind. Okay. Okay, so if you do that, then actually what we get, since epsilon is very small, actually by our choice, H0 plus 2 epsilon, actually it's less than A star star, strictly less than A star star by our choice. So that means I have this a priori estimates, which is that this is bounded below, uniformly bounded below by a positive number. So that immediately passes over to the right-hand side. Okay, so you get an uniformly positive lower bound on this probability. That tells you that A0 plus epsilon is at most the A star star for phi L. You apply the similar thing with the appropriate event, the 2, okay, for H equals to A0 minus 2 epsilon, I think. And similarly, by doing the similar kind of thing, line of reasoning, you'll get A0 minus epsilon is bigger than or equal to H tilde L. Now, which two immediately contradict the fact that, you know, we just saw that they're equal unless epsilon is 0. Okay. So that's how actually from this proposition, you know, in a sense, you obtain the two parameters the same. Any questions for this part? Probably I'll be too fast. Okay, so in the rest of the talk, actually, I'll actually give a sketch, the proof of this proposition. Okay, so let's introduce some scales, actually, because we'll do one step at a time, as I was mentioned in a title of a previous slide. So let us consider a geometrically decaying scales, and let xi n denote the difference between phi truncated at two successive scales. Okay. So by the definitions, actually, they're all independent, of course, and again, they are of range. The xi n actually, their range is exactly ln. Okay, and you have all the nice properties. You have FKG for the signs. Those you have, and by just using a standard hit kernel estimates, we can just prove that the variance is actually decays polynomially. Don't bother much about exponent. Actually, we can do with anything that is bigger than 0. Decays polynomially with the scale, and so it's actually so this another way of saying that this phi lns actually approximate your field phi very well, at least in a polynomial size box. Okay. So now the approach that we'll take here is the following: that instead of hopping directly from a truncated field to the full field, or even between successive truncated fields, we'll pass smoothly, by continuously between them. So what we do is that we introduce an interpolation between the fields, truncated fields at two successive scales, with t denoting the interpolation parameter. So t lies between 0 and 1. So you can think of, as t as regulating the amount of new scale that is being added. And let's look at this function, which is just the probability of connection at height h with the corresponding to the parameter t. Okay. Now, if you think about it, what we want to prove actually, if you think about the statement of the proposition, so what we want to say is that the effect of changing this parameter, scale parameter, you can say that t can be compensated by shifting the height parameter by a very tiny amount. Okay, that you can, and that just amount is just required to be summable. That's all. Okay, so that they, when they accumulate above a certain scale, they're very tiny. That's the reason. That's it. So that's what we want to do. We want to be able to show that the effect of changing the scale parameters, is way weaker than the effect of changing the height parameter. And to do that, we actually, in this taking inspiration from this paper by Aizenman and Grimmett in the 1990s, we use such procedures, and also a bit from our last paper, Duminil-Copin, Severo, and Yadin, about non-trivial reface transition for general graphs using Gaussian free field. So what we do here is that we pass to the differential form of that, what we just said. So what I just said can be translated into saying that, well, it would be ideal if we could show that the partial derivative of this function with respect to t is very small, corresponding to the partial derivative with respect to the height parameter. The negative sign is because, again, recall that as h increases, your percolation the model becomes thinner. Okay, so let's look at their expressions. So what do they look like? And so these are the versions of Rousseau's formula, from Bernoulli percolation for arbitrary fields. And let me tell you that this formula do not require your underlying field to be Gaussian. Okay, they're just true for if you're considering any field which has a non-degenerate density. Okay. So the Bernoulli percolation, they also involve the probability, this event called pivotality. So let us recall that, which I had tried to represent this diagram. So point X is pivotal for this event if, so whether, if it's open, if the vertex is open, you have this open arms stretching the two sets. So you connect, you end up connecting the two sets. Whereas if it is closed, since the closed dual surface passes to this point, these two sets become disconnected. So the point X is crucial for connecting these two sets. Okay, so that's the derivative, and this is just the density of phi t at h. These terms are the constant order; they don't actually play much role. Basically constant. So what is the partial derivative with respect to the time parameter, the scale parameter? So here you have a correlation term, kind of, between the pivotality event and the field, this difference, this xi xn. Remember, which has range L. Okay. Now imagine for the moment being that we are in a very ideal situation like Bernoulli percolation. So there, well, if you again recall or paid attention to the definition of pivotality, the definition itself does not depend on the state of the system at point X itself. Okay, so if you had independence like Bernoulli percolation, it will be immediately, the event pivotality would be independent of anything that happens at X, in particular whether the vertex X is open or not. So if that was the case, then, well, we'd be just able to decorrelate, factorize these probabilities. They'll be factorized into the, I'll take the absolute value on both sides, and they will factor these probabilities, these expectations basically, would factorize into expected value of the absolute value of xi xn, and the probability like this. And recall that xi xn is very thin, like very small variance. So actually we get even better. I mean, so when I'll factorize the prefactor that this will give rise to, comparison to the terms which are basically this sum, that would be very small. That would be even actually exponentially instead of just 1 over n squared. And they will be done, just over. Okay, we have proved. Now, of course, that's not true. The xi-n's have range of dependence ln, and that's as big as it could be, right? N is anything, and your pivotality even is it depends on it's very much there within the box of radius ln. So what do we do? Well, we want to push a bit. Let's try to push a bit in this direction. Okay, and still don't give up on the hope of decorrelation. Okay, so it's just the same picture drawn bigger. So here, let's do a simple trick. First, just separate the case where actually we know what to do. So when my field value is not big, then actually I can just, okay, actually there should be probably an epsilon, but anyways, whatever. Then actually I just can forget about that. They actually have what I need. So the problematic part is really the tail part, right? This is that when the field value is actually bigger than, let's say, what you want, 1 over n squared. And this is the part that we would like to decorrelate. Okay, so how do we decorrelate? Because pivotality even definitely depends on what is happening within your box of radius ln. So what we want to do here is that, okay, we cannot decorrelate pivotality, but let's say we replace this event with an event that is slightly bigger. Okay, in the sense that which will retain all the information about pivotality, all the information like that is happening outside the range of dependence of psi, that is outside a box of radius ln. Okay, and then well, we'll be able to decorrelate. So let's be more precise what I mean by that. So let me introduce in this direction the notion of closed course pivotality. Okay, so what we are doing here first of all, we're forgetting that the paths extend all the way up to x. Okay, let's stop them outside the box. Okay, of course we'll have to reconstruct everything, but that is one thing. Because remember, okay, no matter where, even no matter which event we end up being, this has to be an ultimately. Actually, we are going to compare with the partial derivative with respect to h, which involves pivotalities, and so I have to actually reconstruct the pivotal points. Okay, so I have to keep that in mind. Okay, so I forget that. The next thing is that I actually don't really want to forget the dual surface because it's a bit tricky to reconstruct later. But what we can do actually, push away a bit the dual surface outside the box of radius Ln. So how do we do that? We can do that by requiring this box to be disconnected from a bigger box, okay, by paying a price. So, okay, so remember, okay, so here in this expression, what I've done here is that, well, if I replace this by that event, then I can actually factorize that. And this is really the expectation of just by you obtain from Gaussian tail bound of this quantity. Okay, so no matter whatever we are requiring should have a cost which can be killed by this. This is our bet, main bet. Okay, now we can do that paying a reasonable price just because, remember, and here you are using this fictitious regime for the first time, that h is strictly bigger than h tilde. Okay, so we have, probability, it's just polynomial in the bigger size of the box. So this box outside is e to the power polylog. It's just a thing that I can disconnect, paying this price. But that's okay. Okay, fine. So now we probably have to finish, but let me just give me 5 minutes, probably. Is that now actually is the stage where we have to reconstruct the pivotal points, okay? Now, how do you do that? Well, so what is the situation that we have? Well, we have these two sets, two clusters, which are intersecting box of radius e to the power polylog, polylog n. Well, one can say, I can say, propose, okay, here is a proposal. I explored the cluster of one of them, okay, just reveal that. And I extend the cluster of the other set until a point which is just in the exterior boundary, of the other cluster. Thereby, I'll create a pivotal point there, right? Okay, then actually you'll immediately say, wait a minute, first of all, how do you do that? How can you, what makes you think that one can make such connection? Well, there actually I'll say, because, that's a huge cost, maybe. Then actually, okay, I'll say, okay, no, but here actually you will remember that we're still in the fictitious regime. In particular, h is strictly less than a star star. So I have this, point-to-point polynomial lower bound on the connection probability. So that will just cost me e to the power polylog n. That's the distance. Okay, that's good. But the next question is, hang on a minute. You have that bound for unconditional field. And here you already revealed the cluster of one. So that has a huge information, negative information, for example, along the exterior boundary. And you cannot just get away with FKG or, and your field has a range of dependence Ln. So, it's not independent percolation. So how do you do that? How do you probe all the way? Okay, then actually I can come back and say, okay, I don't go all the way up to the cluster, but I can go to until an Ln neighborhood of the cluster. Okay, because my range of dependence is in Ln, so I can do that. Okay, very good. Let's assume that you have until a distance up to a distance Ln now. Now that's exactly the region where the battlefield begins, because this is exactly the region where your phi t field basically looks like your phi, and you can no longer play this trick anymore. So here actually you really have to do something substantial. And so what actually is involved actually here is that, okay, let me just tell you this. For the moment being, if you even suppose that you have finite, you can locally modify the configuration paying a finite price. In other words, you have finite energy. Forget that you don't have that. Then, one can say that, okay, I can start, if I had a finite energy, I can start by drilling a path towards other cluster. And along the way, I'll pay a price which is exponential in the length, which is Ln. Again, that's not good, because what you have actually to kill that? You just have e to the power minus Ln to the power alpha. And that alpha, let me tell you, for dimension below 5, is actually, this exponent is actually sublinear. Okay, so even if you had finite energy, you couldn't do that. So you have to be a bit more clever. And what you have to do that is that you have to actually instead make this connection using what's called the multi-scale bridge, where actually, you fit a big box between and then geometrically shrink towards the ends. And credit goes to Augusto, who identified it as a quasar, resembling a quasar. And then actually what you will have, well, within each of this box, again, I have the blazing of this estimate. So I can, pick 2 points and make these connections and ultimately join them together, paying again a polynomialize. That's good. Again, you come back to me and say, okay, again, well done, minute. You have actually revealed the 2 clusters, all the clusters. How do you do that? Now actually you cannot play this old trick of going up to distance ln. Exactly there you are. And that's actually a very technical, challenging part of the work, is that you cannot really pick one. Rather, you have to find a good one, good quasar, good bridge, where good is in the sense that, the effect of revealing the clusters, the potential negative information you can get, is mitigated, is ensured to be mitigated within the boxes in this bridge, so that you can perform, you can perform these things that you do unconditionally. And now you see actually why there is an additive error appears in the comparison statement, although in the differential inequality in the ideal picture, there is no scope of that, because you need to assume that these events that you can find stick with breach. Okay, so before I finish, let me just give two credits that the reason actually, okay, so the way actually you prove that such a breach exists with high probability is via sophisticated renormalization scheme, which has its seats shown in these 2 papers, in this paper by Stillman in 2012. He introduced the idea of cascading events and decorrelation by splinking. And precedent of this kind of structure also appeared in the recent paper by Jewitz, Peebles, and Rodriguez. And just finishing with this sentence that, this construction is also very instrumental in proving the identity between H tilde and H, bar that I mentioned in the beginning, in earlier part of the talk. Okay, so I'll stop here.
Okay, thank you very much, Subhajit. So I think everyone can unmute themselves and we can give Subhajit a little applause. Okay, so does anyone have any questions for Subhajit? Okay, there is one here of Hugo. Yeah, which specificities of the GFF do you need?
Okay, so that's a very good question. So okay, what is actually quite important is that, you can obtain, as I was saying here, the finite range truncations, the finite range truncations of the field that we have here. So it's not actually really, it might seem that probably very necessary that to have the decomposition of psi else, but if we can find finite range truncation with a very good local approximation, like the difference of the variance decays like polynomially, that's very good. Okay, so we definitely use FKG property. Okay, in the in this proof. Okay, just to be honest, we also use finer property, which comes from the decomposition of the white noise decomposition of the Gaussian free field to get around some problems with the conditional FKG that we need somewhere. But that can probably be avoided with doing a bit more technical involved work. But yeah, so we use this white noise decomposition, of this field psi else, to enable us to perform some conditional FKG. Yeah, so I'd say that's pretty much it. Of course, and lattice symmetries. Those are there. Yeah.
Yes, there's also a second question from Jacobo. I'm not sure if you can see it. It's what is known for the same kind of questions for the continuum GFF?
Continuum GFF. Okay, so then actually, well, I don't. Okay, so for example, continuum GFF, well, if you just define as such, it's not a function. So you have to make sense of it probably by taking modifications of that. But okay, so what I can say best is that, so for example, in 2-dimension, actually, recent times, people are studying continuum percolation models coming from level sets of Gaussian fields, but not Gaussian free field, but other types of Gaussian fields. Like one prominent example is Brugman-Fock. There are other examples, other classes like random nodal waves. So yeah, so in that case, I think there actually one can ask similar questions. One can try to adapt this technique for those classes, and I think actually Franco is working on that, this kind of thing that extends this, so that you can answer similar questions for those classes of models under pretty generic assumptions. Yeah. So.
Okay.